How much time have you spent looking for parking, only to find that there was none to begin with in the first place? According to a recent study, typical drivers spend 106 days of their lives searching for parking. How can we cut down on this time, giving drivers more time to be where they need, while reducing emissions and keeping it simple? Introducing the Parking Lot Car Counter, a system developed by Chasing Cars, a senior design team in the engineering department at the University of Alabama in Huntsville. Here's a prototype of the Parking Lot Car Counter. Essentially, this system uses image processing to detect vehicles entering and exiting a parking lot or garage and keeps track of the number of available spacing, displaying this to the user. Daytime and nighttime operation allows for 24/7 functionality. Setup involves minimal hardware, which allows for little to no driver interaction. In addition, no pressure plates, gates, or parking attendants are needed. Using a basic webcam connected to a Raspberry Pi, we're able to track various types of objects in their direction. The main tool for doing this is OpenCV, an open source software tool used for real-time object tracking and recognition. This program is coded in Python and runs on the Raspberry Pi. By modifying some of the parameters, we're able to track various vehicles while disregarding pedestrian interaction. A large monitor displays the number of available spots to drivers as they approach the entrance. Nighttime operation involves an auxiliary lighting system, or ALS, which accommodates for less than optimal lighting conditions. This is done using passive infrared sensors, which detect infrared motion. As a car passes, the sensors go off. Combined with an ambient light sensor, which detects the intensity of ambient light, we can determine if our system needs additional light. If so, a floodlight is turned on for approximately 20 seconds via a relay. The threshold value from the light sensor, as well as the amount of time the light stays on, can easily be adjusted in our C++ code. This code is run on an Arduino microcontroller, which manages the auxiliary lighting system. Here's a quick demonstration of our system in action. Here's a quick look at our working prototype. Stephen and Ben are routing the camera wires on the PVC structure for daytime testing, and Kalian is making sure the software is configured properly. The prototype is fairly mobile, with the breakdown and setup of the PVC structure taking about 30 minutes total. As you can see, OpenCV is running in real time on the Raspberry Pi. The car counter can track bidirectional motion of two vehicles simultaneously. Up and down counters in red and blue show vehicles entering and exiting. Notice the car leaving our region of interest. It can be seen in the window labeled Frame, but is not actively being tracked. If you focus your attention on the mask window to the left, you can see there is real-time filtering taking place that detects the car as a non-static object. This shows our system's ability to discern between objects that do and do not need to be tracked. Our system can also detect the difference between pedestrians and vehicles, as shown here. This is a quick look at our tracking software during nighttime operation. This is only a prototype, but a final product would include a permanent concrete structure, weatherproofing, and a larger and more robust display. This project has plenty of room for future development, including power by solar energy, a smartphone application that gives users a quick look at parking availability, and wireless communication between the peripherals used in this project. It can also be tailored for more applications such as security, military use, and production line monitoring. Thanks for giving us the opportunity to share our senior design project with you. From the engineering department at UAH, we hope you enjoyed. Sincerely, Chasing Cars.